Alright, so I think we still remember what we used to do whenever we want to indicate if something, or to indicate the molecular geometry of a given compound. First of all, you have to draw the Lewis structure of that same compound. Secondly, you have to find the electron domain geometry, that is a parental shape. Then that's when now you go to the issue of finding the number of items. The number of items are the ones that helps you find the daughter shapes, that is molecular geometry. That is molecular geometry. So if I'm to start from this one, I'll start by sketching, or rather by drawing its Lewis structure. So I'll say the first thing we said, you have to find the valence electrons. So we are going to have 5, that is for nitrogen, plus 3, that is for hydrogen, multiplied by 1. Total number of valence electrons, we are going to get 8 valence electrons. Okay. Now the second point, whenever you are sketching what we call the Lewis structure, is to do what? You need to find the central atom. Central atom, we said it has to be an element which exists less than the other. So in this case, nitrogen is my central atom. We are going to have nitrogen here. I'll write the remaining atoms in the outermost parts. Let's hope you have that table which I gave you last time. Let's hope we have that table which I gave you last time. Okay. Now the second thing is to do what? You draw a single line in between the central atom and the outermost element. Like this, like that. So we are going to remove how many valence electrons here? 6. So remember, hydrogen doesn't become stable with more than 2 electrons. So it is already stable. Why? Because we have 2 valence electrons in every bond that is being formed here. So meaning that the remaining electrons, if you say 1, 2, 3, we are going to have 6 electrons removed. So whenever you subtract, we say minus 6 to this, we are going to have what? 2 electrons remaining. So these electrons are going to be put on the central atom. On the central atom. Remember, this has to be what? Your Lewis structure. Now you come to the issue of determining the total number of items, so that you can know the parental shape, which is the electron domain geometry. We said for you to count the number of items, you first look at what elements, how many elements do you have in the outermost part. So the total number of items has to be total number of elements plus the lone pairs found on the central atom only. So here we are going to have 1, 2, 3. So I'll say 3 elements. How many lone pairs do we have? We have 1 lone pair. Total number of items, we are going to have what? 4 items. 2 items, the name given to 2 items, to anything which is having 2 items, we say it has to be linear. That is the parental, or rather the electron domain geometry. Something which is having 2 items, we said it must be what? Linear. Something which is going to have 3 items has to be trigonal, planar. Anything having 4 items, it must be what? It has to be tetrahedral. So meaning that the parental shape for this one, or rather parental shape has to be what? Tetrahedral. That is the electron domain geometry. You say tetrahedral. Like this. For tetrahedral, to find the angle, we said you can only find the angle for tetrahedral by saying theta must be equal to 109.5 minus 2.5 multiplied by the number of lone pairs. If you don't have lone pairs, you are going to say 0 multiplied by that. If we have lone pairs on the central atom, you are going to put the same lone pairs on the part where there is number of lone pairs. How many lone pairs do we have here? We have 1 lone pair, meaning that I'll multiply 2.5 multiplied by a single lone pair, and theta is going to be equal to 109.5 minus 2.5 multiplied by 1, we are going to have 2.5 here. 5 minus 5, we have 0, say point. This you subtract from 9, you are going to have 107.30 degrees. This has to be the angle geometry, or rather, the angle geometry for this same compound. Okay, now to find the molecular geometry, we have that simple table which was given. Tetrahedral. If tetrahedral is having a single lone pair, that is what we call, if a tetrahedral is having a single lone pair, its molecular geometry is given by the name which is what? Seesaw. That has to be the name of a tetrahedral that is having what? A lone pair. If a tetrahedral is not having a lone pair, it has to obey the actual name for the same what? Electron domain geometry. Meaning that the electron domain geometry, if it is tetrahedral, even the molecular geometry has to be what? Tetrahedral. Why? Because we are lacking the number of lone pairs. If we have 2 lone pairs, I think we still remember what I said. Having 2 lone pairs, we said seesaw is going to go with what? T-shape. From T-shape, we must go to what we call, a seesaw has to go with, the first one has to be bent, okay? The second one has to be seesaw, and the last one has to be bent also if you have 2 lone pairs.